I'm coming from IAST. IAST, just an introduction. What is IAST? IAST is an Institute of Special Purpose. This is under Department of Space. So basically, we are working together with ISRO. Abdul Kalam sir was our first chancellor, and then U R Rao sir, and then current chancellor is B.N. Suresh, and our current director is the director of VSSC, Dr. Unikrishan Nair. So we have the same director at the moment. So it's a small institute actually, only 800 undergraduates and 120 PhD students, like that. Okay. So on an average, 2 PhD students per faculty. That's our method. Okay. So my research area is, my research lab is called Emerald. Okay. So we chose Emerald out of these 3 words. And the main reason is that I am working mainly on atomic layer deposition, that is ALD. Okay. So that's why we put that name like that. So basically, we are working on different classes of materials, mostly semiconducting materials. Okay, so like 2-dimensional materials, all type of oxides are there, silicon is there, and then using that we basically work on data storage and neuromorphic technology, which is a technology which is imitating our brain, how neurons are working. We can do a lot of logic circuits for future computers. Okay, next time we will talk about that. So it's basically artificial neurons. Okay, and then thin film transistors, because data storage and transistors, because getting data is one thing, storing data is one thing. We have to get the data as fast as possible. So we need faster transistors. So we work on that also. All these things involve basically material science. Okay, so that's why we are using scanning tunneling microscope (STM) to understand the materials, and we can study the materials, and then using those studies we can understand the electronic properties of the material. STM is not for imaging purpose for us. Okay, we can actually do a lot of spectroscopy things. We can measure a lot of things like work function of the material. We can check whether a material is P-type or N-type. What is the band gap of the material? All those things we can do with the STM. Okay. Normally STM scares people, okay, everyone, because STM is not a very simple thing. If you are doing STM, you have to know what you are going to look at. Okay. Without knowing, if you are looking at images of STM, you may not understand that. Okay, or you will interpret wrongly. So those things can happen. For example, you see this is an STM image of graphene. Okay. We know graphene are hexagonal structures, right? But that's not exactly what you see here. You see triangles here. There's a triangle, there's a triangle, there's a triangle. Okay. The reason is that, I will explain when we talk about STM images. The reason is that 3 atoms in hexagon, okay, this hexagonal structure is there. If there are more than one layer of graphene, what happens is that the lower layer will pull down 3 atoms. So 3 atoms are down and 3 atoms are up. That's why you see these 3 atoms are up, that's why they are brighter. Okay. And the other 3 atoms are actually darker. So that's what I was saying. So if you are not careful, we will misinterpret the STM images. Okay, these are carbon atoms. Okay, this is a new STM we installed recently. That's a dot and brush STM, with which we can actually see much more resolution. Okay, we have more resolution and we can see atoms very clearly. Okay, yeah. So that's what we do, and these are the PhD scholars. I have 6 PhD students at the moment, and 1 postdoctoral fellow. They are all doing, basically this person is the STM person. They are all material science and the memory guys. Okay. Let's start with, okay. So, we have to, if you want to believe in science, you have to see. Okay. Not always correct. we don't see many things, but we believe it. Okay. But this is the what's called the basic code for microscopy. Okay, so again, as I just told that don't believe what you see. Okay, that's a different thing. So there's what is about scanning tunneling microscope or atomic force microscope. All what you are going to see is the surface. Okay, you cannot see beyond that, because you are scanning on the surface, and what all you are going to see is only the surface. Then why surface is so important? Why STM and AFM is so important? Because this is the reason. Okay, this is also a quote from surface and interface scientists. Okay, God created, just a word, because the crystal structure is perfect. But when you come to the top surface, everything is missing. Okay, because you see there are a lot of dangling bonds on the surface. When you come to the surface, all atoms are, in the bulk, all atoms are nicely arranged. But when it comes to the surface, what happens? There are no bonds beyond that. We know that, simply speaking, that's why, for example, copper is oxidizing. Right? If you polish copper, after 2 days, it is that polishing is gone. Because copper oxidizes, aluminum oxidizes, silver oxidizes, gold doesn't oxidize. Okay. So depending upon the type of material, the surface atoms have a tendency to react. Right? So the surface is the most important thing in many cases where chemical reactions take place. For example, surface free energy decides whether that material is hydrophobic or hydrophilic. Right? High surface free energy means the surface wants to reduce the energy, so if you put a drop of water there, the surface will try to stretch it and the water will spread over. So you have hydrophilic surface. Low surface energy means it doesn't care. Okay, so water will remain as a droplet and you have hydrophobic surface. So again, surface free energy tells you what type of a material it is, whether hydrophobic or hydrophilic. Now atoms and molecules attach and form crystals, epitaxial layers, right? The growth of crystals from one plane, all those are decided by the surface structure, surface atoms. Yeah, this is what I was saying. There are a lot of dangling bonds, that means unsatisfied or unsaturated bonds on the surface. They are the reason for chemical reactions, right? So this is why surface and interfaces. Okay, what is interface? Interface is just two surfaces brought together. Okay, if it is two different materials, we call it a heterojunction, or it's called a homojunction. Okay, so we have interface means two surfaces, we put them together. And for the fabrication of any and every device, whether it is optical device or mainly electronic devices, you need interfaces, right? For example, if you take a piece of silicon, that is not a device. You have to connect two leads, and then you have metal silicon contact. So there is an interface in picture. Okay, so any interface, any surface leads to interface. Without interface, there are no devices. So that's why surfaces and interface that tend together is a huge area of research. Okay, there's a journal called Interface Physics. Okay, and interface, surface and interface. Okay, very high impact journal. Okay, all these STM results from most of the new results are actually published in that journal. Okay, very good journal. Yeah, so if you want to look at the surfaces and the atomic resolution, to see atoms, you can actually use a very famous method, right? The transmission electron microscope. I think that's a class on TM, right? No, that's not TM. Oh, because it's hands-on. So transmission electron microscope you can actually use to look at the atomic structure of materials. But what you see in a transmission electron microscope are or is actually not atoms. Okay. Is it? Because this is an image from my own paper. So you see, you can actually beautifully see that atomic resolution, right? So these individual things are atoms, and what you see between them is atomic planes. So we can actually see, if you look at the atomic planes, we see 3.1 angstrom, and look back to X-ray diffraction, and you can see which one corresponds to 3.1 angstrom. Then you can see which lattice plane it is, whether 111 or 100 or 120, whatever it is. Okay. But how do you get this image? Is it really atomic resolution? We call it high resolution transmission electron microscope, but we don't see atoms in TEM, honestly. All what we are getting is an image like this. Okay, because we put a sample inside and there is an electron beam coming perpendicular to it. So when the electron beam hit the sample, you get you get a diffraction, electron diffraction pattern there. And that is this diffraction pattern. This is all what you get, for example, like this. Okay. This is what you get from a transmission electron microscope. Now, this is called the selected area diffraction pattern because in a small area we can do electron diffraction. Okay, so this is an area, a small selected area. You see, this is only 2 nanometers. So that means this may be around, say, 15 nanometers or so. So in that area, if you do an electron diffraction, we get a diffraction pattern. And we can see diffraction is a Fourier transform, right? I mean, we call it like that. Mathematically speaking, from what you see here is basically the structure of the grating, which is the crystal. Okay, if you see hexagonal like this, that means the crystal also has hexagonal symmetry. Okay, it may be graphene or graphite or something like that. Okay. It's basically from graphene or graphite. Okay, so you see hexagonal structure means that crystal also has hexagonal structure. Now, what people do is that they take this diffraction image and do an inverse Fourier transform. Okay, then what they get is that they get the grating which gave this diffraction pattern. So basically, it is a crystal which gave the diffraction pattern. So you get back the grating. So if you just take these points, 6 points, and all these points together, and then you reconstruct the image back. That's what transmission electron microscope is doing. It is not giving you atomic resolution. Okay. This diffraction pattern was obtained by this grating, which was a crystal. So you get this one, and you do an inverse transform. You will get this image. Okay. And most of the image you are seeing like this are a little bit fake images, because you can see there are a lot of spreading here, right? This is a larger one, this is a smaller one. I can actually select using a software. I can select a small area. Okay, I can avoid all type of noise from here. I'll get a beautiful image like this. Okay. Normally people won't do that. It takes some time to filter it and do a modification of the. So what I'm saying is that transmission electron microscope doesn't give you a real atomic structure. What you are getting from TEM is basically the positions of atoms, basically. Okay, so it's positions of atom. You don't see an atom. Okay, what it looks like an atom is basically just a reconstruction of the diffraction pattern. So it is basically the position of atoms. Okay, that means lattice points or something like that. That's where we have to look and see. I mean, our idea is not to see atoms. That is an ultimate microscopy technique to see an atom. More than atom we cannot see. Okay, because electrons, we cannot really see electrons. We can only see electron clouds. Okay, that's what we actually see from scanning electron microscope. Okay, scanning tunnel microscope. So if you want to really see an atom, we have only two ways, right? So we have an atom. How can we probe an atom? How can we see an atom? Okay, there are only two ways. Either pick up electrons from that. Okay, so you have an atom. You come with a probe and measure around the atom and pick up electrons, and then you can actually measure what is the size or what is the shape of the atom. Or you just use the force between atom and another force measuring unit. Okay, a cantilever, for example. So when you come closer, what happens? There is interaction between the atom and the cantilever that you can measure, because cantilever has a force constant K, spring constant. So if the cantilever is vibrating, you know how much force is there. That is what is called AFM. Atomic force microscope basically uses the force between atoms and a probe, and scanning tunnel microscope basically uses the electrons which are coming out of atoms. Okay. There's one important thing. If you just take any metal, okay, metals are conducting, we know, right? But if you take just one atom of a metal, you just take one atom from the gold, okay, that is not conducting. That's a perfect insulator. Okay. Because gold is conducting, because if you put more gold atoms together, what happens is that it forms band, okay, valence band, conduction band, then only it starts conducting. If you take just one single gold atom, you need almost 6 electron volt to remove the orbital, the last orbital electron. Otherwise, what happens if there are 100 gold atoms, these electrons actually can go through this the crystal, but if there is only one single atom, it's a perfect insulator. Okay, so that's basically the problem with picking up electrons from atoms. Okay, that's not an easy task. Now we are going to see STM. So how can we measure the surface? How do we image the surface, or what all we can do further with an STM? Okay, scanning tunneling microscope. You see, as I told you before, to use electrons as a measurement strategy, what we have to do is that we have to contact a tip here and pick up electrons from here. Then you will get the electrons. You had a lecture on XPS, right? So there you understood that valence electrons are easy to take out. Inner electrons, right? Core electrons are very difficult because their energy levels, the bound states, the binding energy is very large. It can go from 100 electron volt to 1000 electron volt depending upon the atoms. So all what we can do is to pick up electrons from the valence band or valence orbital, last orbital. Okay, we are not talking about any other electrons. We cannot talk about any other electrons in microscopy because we need high energy to pluck out electrons from the inner orbitals. So we are all talking about the last orbital electrons. And if you want to take out electrons, we just apply voltage, right? Like a multimeter, we just take a probe, apply voltage and take out electrons. But is that really possible? That's the question. Okay, if I take a gold surface, if I use a tip here, suppose it's a, you see now in my diagram, the tip is sharper than the atom. Okay, that's not possible. Atom is the smallest one. So finally what happens, I have to measure, if I want to measure the electrons from this atom, I have to use another atom, right? So I can use a tip, but at the end of the tip there should be only one atom. Then only I can measure atoms, right? Otherwise it is like if you want to measure the size of an ant, we cannot use a meter scale, right? So it is like that. So the tip has to be very sharp. So theoretically the tip is atomically sharp, very, very, very small tip. Now what happens, if I touch the tip here on the atom and I apply voltage, what will happen? Gold is conducting. So all the electrons from all the, this is what I said. If you take just one atom, that's an insulator. But now I have a collection of atoms here. So the atom or the electron which corresponds to this atom will not be here. It will be flying around inside the crystal. Okay, that's why it is conducting. Okay. Now what happens if I just touch the tip on this atom? All these electrons will rush through that particular contact. Okay. So if you look at the current density, if that happens, okay, we are talking about one atom. Okay. Say the radius of an atom, say 10 raised to minus 10 meter. Okay, 1 angstrom. Area means 10 raised to minus 20 pi r square. Okay. So just I'm approximating as 10 raised to minus 20. Now if I am flowing 1 nanoampere current, very small current, suppose, through it. So 1 nanoampere, that's 10 raised to minus 9. So then the current density becomes current divided by area. So 10 raised to minus 9 divided by 10 raised to minus 20. So 10 raised to 11, okay, ampere per meter square is the current that's going to flow through that contact. Not only this contact, the entire thing will evaporate. Okay, if such a large current pass through, and we cannot afford it because our electronics also will burn. Okay. So atomically sharp contacts are very dangerous in that sense. So we cannot just touch an atom and measure the electronic states like that. So we need a barrier in between. Okay. So that all the electrons will not just rush through, but I need to measure only that particular atom. What can I do? I just lift the probe like this. Okay. So it was touching. I just lift it. Now what happens? There's a barrier. What is that barrier? That is basically the gap, the air gap or vacuum gap. Okay. So now this gap prohibits all these electrons to simply pass through. This is where the quantum mechanics comes into picture. Okay. Now we have electrons which are accumulating here in this atom. Now I am talking only to this atom, not all the atoms. Okay. So electrons will come here from this atom and it wants to go to this. For example, suppose I have given positive on here and negative on the gold. So these electrons want to jump to the positive side, right? Electron always go to the positive. Then what happens? It cannot go because there is an air gap. Okay. So now, if this distance is smaller and smaller and smaller, what happens? Quantum tunneling starts to happen, right? Earlier times, people used to use when this electron starts tunneling, we will get a small current in the circuit. And earlier times, what people used to do when they are doing STM is that they use a headphone, okay, and then they slowly bring the tip down and down and down and down. They don't hear anything except noise. But as soon as the electrons start jumping by tunneling, they start hearing a noise, okay, a kind of a humming sound because of these electrons, okay. So people used to say that this is for the first time I heard the quantum sound of electrons. It's not every sound is quantum sound of electrons. Okay. But they used to say that now electrons start tunneling. But now we have very sophisticated electronics which will tell that the electron starts jumping. So the number of electrons jumping from an atom is very, very small. So usually we get something like 10 raised to minus 10 ampere. Okay, very small current. And then we can use an amplifier to amplify it. Then we will get a decent current. So we amplify it and get the current. So this is basically the the principle of STM. This is all about STM. Okay. The rest is just electronics. We use an amplifier here and then amplify the current. Now, okay, I can actually show you a small. So at any width of the barrier, there is a finite probability for the electron to transfer. Okay, now you see, I am going to reduce the barrier. Once in a while, electrons start jumping in, and as it goes thinner and thinner, more probability of electrons to pass through. Okay, got it? I just so I am reducing the barrier, the thickness of the barrier I am reducing. So the probability of electron passing through that barrier becomes larger and larger. Okay. Actually, in principle, theoretically speaking, this is exponential. Okay, exponential to the width of the barrier. Now, in STM, what is the barrier? That is basically the air gap. Okay, which means that I have a tip, I have a surface. If I bring the surface, the tip closer and closer to the surface, what happens? The probability of electron jumping from tip to the surface or back, depending upon the polarity of the voltage, will exponentially increase. Okay. So I am just going to show you 2 to 3 slides on the theory of tunneling, which you already know, just to refresh. Okay, then you will understand that this barrier height is exponential to the current. Okay, so if you just go up, exponentially the current will go down. Okay, and that also is a very important information. The current which goes exponentially with the height from which we can actually estimate the work function of the material. I will come to that, and that's called the IZ spectroscopy. Current is the vertical distance. Okay, IZ spectroscopy. Okay, we come to that. Now we have the atoms here. Okay, these are atoms. This is the tip. Now you see I brought very close so that electrons can jump. Okay, these are the electron waves. So you see between atoms it doesn't pick up anything. Only on atoms it starts picking up electrons. Okay. Now you just measure as a function of the distance or the map, you just map the current here. Okay, so when you get the electron from here, you get a current. This is a pixel. Okay, and next atom, next one, next atom, next one. If you do this, you get a two-dimensional map of the surface. Okay. Yeah, this is all about STM. Okay, so what I mean is that there is nothing to be scared about STM. Okay, so STM is a beautiful instrument. It's difficult to work with because you need to get this resolution. You see, what we are going to do is that the tip will be one atom away from the surface. Okay, so the distance between the tip and surface will be only a few angstrom, 1 nanometer, maybe 10 angstrom. So while STM is running, if you are just walking through that lab, the tip will crash. Okay. So there you need a very proper vibration isolation, all those things you need. Otherwise, other than instrumentation, the STM is a simple and very useful technique. Okay. Only problem is that this has to be conductive. Okay. Only conducting materials we can use for STM. Semiconducting also is okay. If you get some electrons through it, that is fine. So biological samples, very difficult. Okay. Unless you give very large voltage. If you give large voltage in biological or soft samples, it can burn. Okay, it can damage the surface. So mostly that's the limitation of STM. It is useful only for conducting and semi-conducting samples. Insulating samples, oxides, all those things, you can really use it. Okay, otherwise that sample has to be extremely thin so that electron can still tunnel through it. Okay, then it is possible. Okay, I'll just quickly go through it. This is just a refreshing thing. Don't worry about the huge equations you're going to see here. You have already seen that in the MSc level, but just what happens, I'm just applying negative here and positive here. Electrons will move, classically speaking. So that movement of the electron, now we just use Schrodinger equation, right? So using Schrodinger equation, this is the tunneling problem in our quantum mechanics. Okay, so quantum theory, tunneling is a standard problem we solve to show that how Schrodinger equation is used there. Should I explain this or I mean do it? Okay. Yeah. So what is this equation? This is a Schrodinger equation. This is a time independent Schrodinger equation. There is no time in it. So it is basically for a steady state. This is the wave function of the electron. This is the energy of the electron. If there is a potential, if we are applying a potential, that is the V, and N is the mass of electron. S cross is the modified Planck constant. Okay. So now this is our situation. This is our Schrodinger equation. We have a barrier here, and we have collection of electron here. We have nothing here. So suppose I am applying negative here and positive here. What happens? Electron will move in this direction. If electron is moving in that direction with say psi, this is like a wave function which is like an amplitude of the electron wave. Okay. Electron is coming here. Now what happens? Here there is no potential. This is the potential barrier or the barrier. Okay. In barrier physics we call potential barrier because the electron has to penetrate through. Okay. So it's a potential wall. This is a free space. This is a free space. Only potential is only here. So what happens? Electron come here. There are two things that can happen to the electron. Either it can actually reflect back. Suppose this is just a wave. It can reflect back or it can transmit through. Okay. So since there is no voltage here, potential here, V is 0. So this equation is now reduced in one dimension. Okay. Just reduced to this equation, V equal to 0. And so when electron is coming and going back, so we have a solution for this. This is a second order differential equation. So we have a solution which is actually, this is a e raised to ikz is the coming wave, and when it is going back, e raised to minus ikz. Okay, so we have an incoming wave, reflecting wave. Okay, don't worry about this. Okay, I mean you don't have to write it down. Just explaining what is tunneling. Okay, so in this wave can reflect back. So we have two solutions. This is the wave which is going here, and this is the wave which is reflecting back. And this k is from here. This is the 2me divided by s cross. That's what is this k. Okay, from this equation. Now on the other side also, there is no potential here. So what happens? Potential is not there. So we have this equation now reduced to this equation. Again, the same similar equations there. And there, the wave is not coming back. It is just going in one dimension to the infinity, right? So we have only one solution here, that is f e raised to ikz. E raised to ikz is a plane wave which is actually moving in space. Okay, so it's a plane wave which is coming. Since it is reflecting back, we have incoming and reflecting parts here. Since it is only going in one direction, we have only the transmitting part is there. What about inside? Inside we have this potential is there. So if you get the solution for that, you have to solve this equation with the potential also here, and if you solve it, okay, this will be this is the solution of this equation will be c e raised to I is not there, c e raised to just because it is exponentially going back, okay, going down, and then it is transmitting to the other side. So if there is an I here, e raised to I alpha z means it is it's a wave again. It's not that wave; it's an exponentially going down wave. So inside that potential, the electron is just simply coming from one side, and then it is slowly damping and going to the other side. Okay. So classically speaking, classical electron, if we consider electron as a particle, this doesn't happen because particle comes here and bounces back. It never goes to the other side. But quantum mechanics says that there is a finite probability of going to the other side if you assume that electron is a wave. Yeah. So consider only this part. Okay. Now what happens? A constant into e raised to a constant z. E raised to minus k z is the main equation we all have to worry about. Okay. So what happens? What is z here? Z is the distance of the width of this barrier or the distance between the tip and the sample. Okay. So that means if the tip sample distance is reducing, more and more tunneling probability, because if z is smaller and smaller, larger will be the wave which is passing through. Okay, so from here we can actually find out what is the transmission coefficient and reflection coefficient. Just like when you shine light on a glass, it reflects back and it transmits. So that's a transmission coefficient, that's a reflection coefficient and transmission coefficient. That also we can identify in terms of these constants. Okay, so reflection coefficient, since it is coming and going, that's b square by a square, because b square is the reflecting part, a is the incoming part. Okay, so reflecting part divided by incoming part gives you the reflection coefficient. That means what is the probability of electron which is bouncing back. Okay, and similarly here we can actually get this is the incoming wave, this is the transmitting part. So transmission divided by incoming gives you the transmission coefficient. So this actually shows that, this part actually shows that there is always a finite probability. If the potential is not infinitely large, there's always a finite probability for the electron to pass through. Which means that if I take 1000 electrons and I am throwing to a wall, what happens? If the probability is 1%, I have 100 electrons. No, 1% means? Yeah, right? Or it is 1% of 1000? 10. 10 electrons, yes. 10 divided by 100, yes. 10 electrons can pass through. Okay, if the transmission coefficient is 1%, which means that if I am throwing 1000 electrons to a wall and I am saying that transmission coefficient is 1%, 10 electrons will go. The rest of the 990 will reflect back. Okay, and that 10 electron is sufficient for our microscope. Okay, so now we have this tip coming here and coming closer and closer according to the equation e raised to minus a constant into z. Okay. Let's say e raised to minus k d. D is the distance. Okay, so as I go smaller and smaller in d, more and more exponentially larger number of electrons I will get. Okay, and this is what I was telling before. This equation will come later. This alpha, which is this, forget about this term. Okay, only this term is sufficient for now. So this is e raised to minus a constant into that distance between the tip and the sample. Okay, that is basically the current, tunneling current we are going to get. Now this contains a voltage, and this E contains the work function of the tip and the sample. Okay, that's where we do the spectroscopy. Okay, basically that equation we use to do spectroscopy of materials, and I will show you that later on. So AFM also can do spectroscopy. Okay, we'll come to that. That's called the Kelvin probe microscope. But when STM does the spectroscopy, it is called IZ, because that it's basically between current and this Z. Okay, we are measuring the current and reducing the Z, so we'll get an exponentially increasing current, from which if you just fit a curve there, you will get what is alpha. Okay, exponentially fitting, you will get an alpha. From alpha, we know what is mass of electron, we know what is H cross, and we know what is the voltage we apply. We get directly the work function of the material. Okay, we'll come to that later. Okay, so this is the transmission coefficient in the full form. So which means that if a wave is coming here and if there is a barrier, there is always a chance of that wave to go to the other side. That is what is tunneling, right? Yeah, so okay, these are all just imaginations of tunneling, and these are all simulations of tunneling. Electron is coming, I don't know whether you can see a small part of the wave is actually like a ghost, it is going here. Okay, so that's these are all simulations of tunneling. This is all what we need. The transmission coefficient is proportional to e raised to alpha into L or D or Z. Okay, that's the distance between the tip and the sample. And alpha is this constant. Okay. So just keep that in mind. Okay. So that's all about it. And tunneling. Now what happens? Suppose E minus V, that time is 1. Just I'm arbitrarily taking. Suppose it is 1 electron volt. And alpha, if I take this as 1 electron volt, if I calculate this, alpha will be this value. Doesn't matter what it is, but this value. And suppose the current, okay, what current is that? I put the tip and the sample here. I have applied a voltage. There is not only tunneling, there can be thermal jump also. Okay, a little bit of thermal jump also can happen. That's called the thermionic emission. Okay, so some noise will be there. And if I take that noise as 1 nanoampere, it's huge, but for STM it is a huge noise. Suppose I take these values. Okay, 1 nanoampere here. I took this value as this one. If I assume E minus V as 1 electron volt, then if I measure the tunneling current, okay, like this, so I know what is this distance, all those things. Tunneling current will be 10 raised to minus 54 ampere. Okay, that means we have to wait, after 1 electron passes, we have to wait the entire universe to completely start over million times, then only next electron will go. There is no way to measure this current. Okay, we cannot measure this current. 10 raised to minus 54 ampere means, right? So we cannot measure that current basically. So if I reduce the sample distance to, instead of, this is when 20 nanometer, okay, if the tip is 20 nanometer away, that is the current. If the tip is 2 nanometer away, you see the current becomes very small, exponentially larger current. So 10 raised to minus 40, that is something we can measure. Okay, Very difficult, but we can still measure. A femtoampere we can measure. Okay. So
this polarity is correct, by the way.
Sorry.
Okay.
Polarity can be both ways. Electron, if it is like that, electron will jump from the tip to the surface.
Yeah.
If it is reverse, it will jump from surface to the tip. That's all. And the information you are going to get is different. I'll tell you. Okay. But both ways is possible. Okay. Yeah. So that means the tip sample distance should be lower than 2 nanometer. 2 nanometer is the size of four atoms. Okay. Sorry. It's possible. It's possible. Yeah. I mean, our technology is now really advanced. We can just keep one atom away. Okay. So we have to go lower than 2 nanometer. Then only a possible measurement is possible. Okay. So the first condition is that it has to be less than 2 nanometer. And if we keep 1 nanometer away instead of 2 nanometer, then you see a picoampere current. That's fair. Okay. So that's the first condition before even start modeling or designing this instrument. This is the first condition. The tip sample distance should be 1 nanometer. Okay. Yeah. So now how are we going to do that? So we have the tip here. You see, this is a very good information because you see the size of the atoms is of the order of say 3 angstrom, 4 angstrom, like that, half a nanometer. Okay. Which means that if there is a variation of height. What is height? Height is Z, right? The tip sample distance. If that variation is of the order of 1 nanometer or 2 nanometer or even less than that, current will be large. Which means that if I am going to scan this tip, you see here the distance is large. But if I put the tip here, distance is small. So I can very clearly distinguish between the current of this area and this area. Right? Because huge difference in the current is there. Because this distance has now reduced. Okay. So exponentially larger current I will get. So I can very clearly distinguish between there is an atom, there is no atom, or if there is an atom on top of an atom. All these things I can very clearly map using this technique if this 1 nanometer distance I can keep. Okay. And as long as I am using maybe for days and nights I am going to scan, all those times that distance has to be same. Okay. So that's the mechanical or instrumentation challenge. Okay. And that's already solved. Okay. That's no problem with it. So theoretically, solving the height of an atom by measuring the tunneling current is possible. That's where it started in IBM in 1980s. The idea that this is possible, we can do atomic resolution. Okay, using tunneling current. Experimentally, you have to keep the tip in 1 nanometer away from the surface. That is the problem. Okay. Basically, this should be a more practical class, but I am just explaining the theory of it because understanding the instrument is more important when you are doing an instrument. Okay, because there can be a lot of errors. I always tell my students, if you are getting an exciting results, first doubt that it is an instrumental error. Okay, so I have written on the board because there are several instances where photoluminescence spectroscopy can give you a totally wrong thesis. Okay, because if you don't know how the PL spectroscopy is working. Okay, so like that, knowing the instrument is very, very important. That's why I'm just giving you all these things. So in IBM during 80s, Henry Rocker and Herb Binning, they came up with this idea. They calculated all these things and they thought that okay, let's make it. Okay, IBM is a place of it's Nobel laureates. Okay, Bell Labs, IBM. So what they did is that they actually thought about a piezoelectric material. Okay. The advantage of piezoelectric material is that if you have, suppose this is a piezoelectric material. Okay. Now what happens? If I apply voltage across this material, it will expand or it will shrink. That is called piezoelectricity, right? Or the other way around also. If I press it, on the perpendicular side, voltage will develop. So they use the other way around. They have a tip like this. Okay. This tip is now mounted on a piezoelectric material like this. So this is a piezoelectric material. That's a sharp tip. That tip is usually either platinum or tungsten. Because when you are applying voltage so close, like I told you before, the current going to pass is very high. Okay. The electric field also is going to be very high. Even if you are applying only 0.5 volt, what is electric field? Electric field is voltage divided by the distance, right? So 1 volt divided by 1 angstrom. See, it will be 10 raised to 10. Okay, it is going to be 1 gigavolt per centimeter. Okay, if you do that, I mean, it will explode, but that is happening there. So at that huge electric field, not voltage is small, but electric field is very large. Atoms can pluck off if you use soft materials. So gold cannot be used. Gold is one of the very soft materials. Okay, so it has to be platinum. Platinum is hard, very hard material. And usually it is platinum iridium, it's an alloy, which is even harder. Okay. Or tungsten. Tungsten is a hard material. So the tip is made of tungsten or platinum iridium alloys, and then it is mounted on a piezoelectric material tube, a cylindrical tube like this. So if you apply this X electrode across that, if you are applying a voltage, what will happen? This will elongate. Okay, this tube will elongate. That means the tip is coming closer to the surface. Okay, or if you reverse the voltage, it will go back. So like that, if you apply microvolts, you can actually get nanometer resolution of nanometer expansion of the material. Okay, so piezoelectric materials are used for approaching. Okay, this is called approach. The tip is now approaching. In AFM also, you will see the sample. The tip is approaching. Okay, the tip will approach the, and then we can actually. So what happens is that if you apply across this will elongate, and if you apply this across X and Y electrodes, what will happen is that this will bend. Okay, so it can actually approach like this, and if you again apply voltage across the other two electrodes, it can bend like this. So now what happens? If I do an AC voltage, it will scan. Okay, now it will scan, and then I can retract it, so I can scan the entire surface. So applying voltage to the piezoelectric material, the tube, we can do scanning. Yeah. Yeah, that vibration you have to take care. Okay, all vibrations you have to take care. But this vibration will be very small. Okay, it is not like I skipped that part actually. It's not in one stretch. It is coming down. It's called a stick slip. I think I have a slide on that. Let me see. This is okay. It is sticking. This is sticking for some time, slipping. So this is how it is actually moving. You see, expanding. So that means it jumps one step. Okay, it jumps one step and stop there. Jump one step, stopping there. Okay, there will be vibration, but when it reaches, so how it happens is that once the tip comes to the tunneling current regime, we call tunneling regime. Once it is there, now we are not going to move the tip anymore. Okay, now the scanning happens. So scanning will be an extremely small area, so the vibration will be extremely small. Okay, it doesn't matter actually. Okay. Yeah.
What is the surface roughness average of this sample?
Surface roughness, you can actually use any surface. I mean, any surface means the height. Okay, I will come to that because it actually depends upon the feedback loop we are giving. Okay, so the scan. This is a common question for AFM and STM. Okay, so I'll address that there. Because the surface roughness, if it is more than microns, what happens is that the tip will go and crash. Okay, and how do we know? What should we know? What should we do then is to scan very slowly. Okay, because okay, I will tell that at that time. Okay, so I have some diagrams about that. So this is basically how it works. Okay, so I will go quickly because our time is almost up. So you see, then if I'm coming, so I'm coming from this. Okay, initially the distance is large, but if I am coming closer and closer, you see almost exponentially. It's not a very good exponential, but almost exponentially the current goes up. So I can actually stop anywhere at 1 nanometer or 0.5 nanometer, and I can start measuring because now I am getting tunneling current. Okay. So now how the system knows that I am already in the tunneling regime? Initially the tip is away, and it comes down, and will check what is the tunneling current. So in the software, I will put that I am applying 1 volt across it. I need 1 nanoampere current. Okay. So initially the current is very small, picoamperes current only. So the tip will go and check 1 nanoampere. No, it will go check, and as soon as it gets 1 nanoampere, it will stop there. Okay. So like that. So this is a very large current actually, nanoamperes. Normally, wherever 1 nanoampere current is there, we stop it there, and then scan with that 1 nanoampere. And for the first time, they actually showed that you see this is a simulation of a silicon surface, silicon 111 surface. If you heat at high temperature, atoms will arrange each other, and it will form a structure called it's like what's called that some cake is there. Its name also is like that. So it's like a small cake, okay, a piece of cake. So this is called the 7 by 7 reconstruction. Okay, so the 7 atoms by 7 atoms is a structure will form, and they could vaguely see that. You see this one. This is the first ever atomic image. Okay, TM doesn't give you atomic image. Okay, this is the first ever real atomic image, which is very bad actually. But you can imagine this was in 1980s. They submitted this result with a lot of interesting results about the current through an atom and all to Physical Review Letters, which is one of the most prestigious journal in physics. The reviewer rejected it, saying that this is just an instrumentation. There is no physics in it. Okay, so I could actually meet Rocker in a meeting in a STM conference in Basel, in Switzerland. So very simple guy. He just comes and sits with us, takes photos, and then he was telling all these experiences. They sent this result to Physical Review Letters, got rejected, and then they submitted this to Applied Physics Letters, another more applied physics. They accepted it. 5 years later, got Nobel Prize. Okay, yeah, Nobel Prize in 1986 for the first ever atomic image, real atomic image. I mean, now comes the question: what are we actually measuring here? So we have an atom. We have the tip coming. Okay, so basically you see the atom is now wrapped with the electrons. Which electrons? The valence electrons. Okay, so the wrap of the valence orbital is what we see as an atom. Okay, that's my next question. What is the shape of an atom? Okay, so shape of the valence orbital is the shape of the atom. Whatever is there inside a gift box, how the gift box is wrapped, that's the shape of that object. Okay, so basically what we are measuring is the electron cloud, the last orbital. Okay, so that's basically what it does. We'll go quickly. This is a more decent exponential curve, which we measured in our lab. It's on zinc oxide. We measured it. So when the tip comes closer and closer, exponentially the current goes. So we can fit using origin. We can just fit an exponential there. We will get this is the exponential factor. This is the d. Okay. From here we get this part, and from there we can actually get E, because we know what is the voltage we applied. And okay, so there are two different modes here. Okay, and that's for the safety of the not the safety of the sample, safety of the instrument. Okay, so now constant current mode and constant height mode. So this is where the sample roughness comes into picture. Constant height mode means that the tip goes exactly in one height. Now what happens if there are variations in the profile? This is going exactly in the same height. So constant height means actually okay. It measures the tunneling current. Now what happens? Constant height, which means that everywhere from the surface it will have constant height. If there is an object here, it will jump up, constant height, and again it will go down. Then what happens? Constant height means current will vary. Okay, because constant height is current doesn't vary, right? It is constant height. E raised to minus k z. Z is constant, so current will be constant. Now, what are we going to measure then? How do we keep the height constant? If you want to keep the height constant, when the tip comes closer, feedback knows that okay, there's a change in the current. It supplies voltage to the piezo, it goes up. Okay, so whatever happens in the feedback, we mark it, we will get a constant height image. And that is safe for rough samples, because samples are very rough. There are a lot of grains or grain boundaries, so it can actually go all along with the same height. See, normally more than a micron roughness, we don't use STM. Okay, and then what happens? Now that's the next question. If it is very rough, like a micron size, see the RMS root mean square roughness is about 1 micron. What happens is that the tip, you see, what I said is that the tip maintains height because feedback is taking it out. Now there is a time constant related to the feedback. Okay, so there is a response time. If I am scanning faster than the response time, what will happen? Before the response comes, I will go hit it. Okay, it's like if I am sleepy and if I am driving the car. Okay, my response time is low, but the car is fast. It will crash somewhere. Something like so. Then what we have to do is that if the sample is rough, we have to slow it down. Okay, the scanning speed should be very, very, very low. The roughness increases. Scanning, this is applicable for AFM and STM. Okay, because other than taking electrons, STM and AFM, all these electronics are the same. Okay, STM is measuring current, AFM is measuring voltage, but force. But force is now converted into voltage again. Okay, from the diode, the photodiode. So basically, all the electronics behind is the same. So feedback is important. If the surface is rough, do a very slow scan. Okay, it may take maybe 10 minutes to get an image, but that is safe for your sample and the instrument. Okay. So that is about constant height, which means that you will get a constant height better for rough samples. Okay, because there can be abruptly different variations on the roughness. So keep it very slow, and constant height mode. You will get good images. Second is constant current mode. Okay, I put it like that. This is constant height mode. This is constant current mode. Constant current means what? I'm actually going here. Now what happens when it comes closer? I have to keep the current same. So again, feedback will apply. So it goes proportionally away. Okay. So current is constant in constant current mode. Height is constant height mode. Okay. So depends upon, constant current mode you can actually use very flat samples. Okay, flat samples like extremely thin samples, graphene, this kind of samples you can use constant current mode. Constant height mode, yeah. No, constant, let me see. Constant height, this is a constant current mode. Okay, so when the tip approaches the step, the current increases. This is that's not constant current mode. I actually put the things opposite. So constant height means that height is constant. Okay, so wherever it comes, height will be in the same. There actually current is changing, but to compensate that current, feedback is applied. Okay, constant current means again feedback is applying, but it has to keep the current constant there. So that the voltage applied to the piezo will change. Okay, because it has to keep the constant height. Okay, so that current supplied to the piezo, if you are mapping, you will get again the same image. Okay, so you can map either the current which you are getting through tunneling, or you can map the voltage which you are feeding to the feedback. Okay, again same with the AFM also. AFM also you can feed either the force, okay, and the deflection you are getting in the cantilever, or you can map the feedback. Okay, feedback voltage which actually keeps the height constant. Okay. Yeah, so this is initial STM which made by Rotor, but this is an STM which we use in Leiden University. That's now very complicated. Okay, because it needs vibration isolation. As I told you, the tip is very close to the surface. Now, any small vibration, even vibration of what I'm speaking, that also will affect it. It will crash. So to keep that, we need all these cushions. Okay, all these pillows, the rubber pillows are there. So all vibrations are suppressed, and all these things are now on top of. We cannot put it on floor now. Okay, we have to create a big well, and inside there should be bars, and on top of bars we have to put these things. Okay, some people actually hang the STM, okay, with the springs, with the large, small spring constant, so that the vibration will be small, damped. Okay, all those things we have to do, and all type of material analysis will be incorporated. So this is the initial resolution of silicon. With this, we can actually get this resolution. Okay. Here we can actually see the diamond cuts. Diamond cuts very very clearly. Okay, so this is silicon again 111 surface, but that's the difference now. Now the question is, suppose we have beautifully arranged atom, but in between one atom is having a different orbit, different electron cloud. What will happen? Suddenly we can see that the current coming from that atom is different. Okay. Suppose this is silicon and in between there is a copper. Okay. Copper gives more electrons. Okay. Because copper is now in silicon, even though it is one atom, it is in the silicon lattice. So it will be brighter. So you see this is normal atoms and there is a bright atom in between. So we can see whether there is a defect also. I think in this image you see some places atoms are missing. Okay, like here. So defects also we can identify, impurity atoms also we can identify. We can actually take the current of that impurity atom alone because we have that resolution. Okay, so keep the tip here and measure the IV characteristics. You can see how much that single atom is going to give you the current. whether it is an N-type impurity or P-type impurity, all those things we can measure there. Okay, this is the question I was asking. What is the shape of the atom? Okay, shape of the atom is spherical. Is only our school time information, but now we know it's S, P, D, F orbitals are there. If a S orbital is the last orbital, that will be spherical in shape. If P orbital, like carbon, 1s2, 2s2, 2p2. P orbital, carbon has the last 2 electrons in the P orbital. So P orbital has dumbbell shape. So we know that if you take carbon, if you image carbon in the STM, you will get a dumbbell shape atoms. But we don't see the complete dumbbell because half of the dumbbell is now bonded below. Okay, so we see one dumbbell like that. And dumbbells are having larger spatial protrusion than sphere. So that's why when you want to calibrate STM, want to measure something to see whether STM is okay or not, you always use graphite. Graphite has carbon, hexagonal carbon. So it's easy to measure the height profile of P orbitals. Okay. Yeah, so this is like that. So S orbital is like this, and this is the next 2s orbital. This is the P and 3s orbital. So S orbitals are difficult to measure because they are spherical. They look like a idvi on the surface. I'll show you some images. So these are atoms of silicon surface. You see, this is a nickel surface. Nickel. This is from IBM image lab. I mean, there's an image gallery, STM image gallery. IBM. You can just search in Google. You will get all very beautiful images. Okay. This is nickel surface, nickel atoms, and this is platinum surface. You see. So depending upon d orbital of the electron distribution, the d orbital, the shape will change. Okay. This is a holmium atom. I think it is a F orbital. I don't know. Some F or D. So again, this is a single atom, but it will be like here or here because F orbital I will show you the F shell later on. The important thing about STM is that, as I told you before, you have to know what we are looking at. Okay. If it is a molecule, suppose it's a benzene or pyridine or whatever it is. Okay. You have to know how it looks like before you're looking at it. Because what you are expecting, if it is benzene is hexagonal, doesn't mean that you are going to see hexagonal atoms. Okay. Because what you are going to measure in a molecule is the total molecular orbital there. Okay. I will show you some examples. You see, this is these hexagons drawn here are actually drawn by hand or by software. The actual molecules look like this. Okay. Because what you are going to see is the molecular orbitals of the molecule. So if okay, this is from our lab, it's again graphene surface. You can actually see the atoms going like that, and from here it's a break. It goes in a different direction. That's a dislocation in the material. This is one single antimony orbital atom. Actually, it looks like 3 atoms, but that is a single atom because the orbital, which is okay. So 5p3. This one. So this green dumbbell is what you see here, and the part of this yellow is what you see here. Okay, so that's what I was saying. We will think that there are 3 or 4 atoms around it, but this is just a single atom. And like that, this is the shape of basically the antimony atom. Okay, so you have to know in advance what you are looking at. See, this is for example, you can simulate this. Okay, in DFT density function theory softwares like Gaussian or Schrodinger or ATK atomic toolkit, you can simulate how these orbitals look like. Interestingly, the ground state of the orbital and excited states are different. They also have different energy, different electron distribution. Because ground state means HOMO levels will be filled up. Excited means LUMO levels will be filled up. So this is how you are going to see, for example, benzene in a STM. Okay, you don't see 6 atoms like this. This is the last orbital electrons, how they form the valence orbital or the HOMO level of the benzene. And you see, this is the real picture of STM. I mean, not the hexagonal one, but this background picture, that yellow and red one. This is if you draw benzene in the wave functions of benzene, how the electron cloud looks like in benzene. This is how it looks like. That's what you see here. Okay. So you have to identify. You have to know already what you are going to see, and then you have to identify. This is benzene. These are actually drawn pictures. this is what you see basically. You see this is a phenyl excited state, I think. This is ground state and so this is excited state. So you see, this is what you are going to see instead of the hexagonal ring. Okay. So you have to identify molecules, you have to do a DFT calculation first and see how the molecule looks like, and then only you can see in the STM. Okay. Okay, this is from our STM. We have already seen. If there are two layers, okay, this is the first layer of say this is molybdenum disulfide MOS2, and this is the second layer. Now there is something called Murray pattern. Okay, Murray pattern is when you have this polyester shawl when you are hanging, you can actually see a pattern inside, and that's this pattern. Okay, so that pattern actually varies with rotating that angle. This is what you see here. Okay, these are not atoms; these are electron localization. Okay, localized electrons, because electrons are now, they are waves, right? So we are actually taking the waves of electrons. We are measuring the waves. So they also have this interference with the atomic lattice. Okay. So if you see beautiful lattice images, but you see the distance is large, much larger than an atom, it's called Murray pattern. Murray pattern. Okay. Murray patterns. That means electrons are localized here. Okay. Instead of spreading all over, these electrons are localized here. There are no less electrons, more electrons, less electrons, more electrons, like that localization. Okay. And this is something called the magic angle of MOS2. At a particular angle, you will get it. And people had predicted it. We didn't know this. Lack of ready. So what happened is that after getting this, now we are not getting it anymore. So we want to publish it, but no, not anymore. We are getting that image. So there is a lot of luck. You see manganese ions on a surface. I think it's on copper surface. You can see atoms here. Okay, single atoms. I'll stop by this. So you see, this is an example given by IBM. This is copper surface on the background, and they put iron, evaporated iron molecule, iron atoms to it. So these are iron atoms, and the background is copper surface. What they did is that they arrange the copper in a ring. Like you go to one atom and apply a voltage pulse, the atom will jump to the tip, and bring it wherever you want, reverse the voltage, it will drop. Okay. So take it, drop it, take it, drop it. You can actually create the entire circle, and what you see inside is it's called plasmons. That's the electron density of copper. Okay, so electron waves of copper, which forms a standing wave inside the fence. The tip comes. Tip is metallic tip, so a lot of electrons are there. Now I have the sample. Suppose you have a thin film sample or a nanoparticle. Now I put it here. Now what happens? I bring the tip here. Since this is a metal and the surface is, insulating or semiconducting, whatever it is, I want to tunnel the electron to the surface, suppose. Then I have to give positive bias to the surface, right? So negative here, positive here. Electron will jump from here to here. Now there are a lot of electrons here, but if this electron wants to occupy the sample, there should be, quantum mechanically speaking, there should be allowed states there. There should be seats for the electron. Okay. Now we know that if you take a semiconductor or an organic material or any insulator, for example, valence band is full. There are no seats. It's a houseful movie. Okay. Valence band is always full. Conduction band is empty. So if I am supplying electron from tip to the material, it can only occupy the conduction band, because valence band is full. I cannot push an electron there because valence band is full of electrons. Okay. Which means that if I am applying negative on the tip and the sample is positive, if electron is jumping from the tip, it will go to the conduction band of the material. And conduction band means what? Let's say excited state. Okay. So that's an important thing. If I am imaging a molecule with the tip positive and the molecule tip negative and the molecule positive, which means that I am supplying electrons to the molecule, it will go to the conduction band of the molecule. Whatever image I am going to get is the conduction band, excited state of the molecule. Okay, so I am giving to the conduction band. Reverse the voltage. Negative on the surface, on the molecule, positive here. Now I am getting electrons from the molecule to the tip. And now valence band is full, I can take electrons from there. So electrons will be coming from the valence band of the molecule. Okay, you are getting the ground state. And this will be totally different. Okay, interestingly. So to know what is the shape of ground state and excited state of the molecule, we have to do DFT calculation. And we have to check whether that is what we are getting. Okay. So again, then you can actually ask, where do we do the STM? Okay. STM is the experimental validation of whatever we see. Without doing DFT, we cannot really do a molecular level STM. Okay. And doing DFT with the Schrodinger or these softwares are it's very easy. Okay. In 10 minutes, we can get the structure of the molecule, whatever I showed there. So the polarity of the tip and the sample determines the excited state or ground state, whichever we are monitoring. Okay, that's an important thing. That's what actually shown here. This is the tip and this is the surface. For the electrons to pass, there should be some available states there. Okay, and so basically this is from the tunneling equations only. This is the number of density of states available here, because it is like a theater we are opening. Okay, people are waiting outside. A movie theater is opening. If it is already houseful, nobody can enter inside. That is the valence band. Okay, if it is empty, we all can go inside, and that's the conduction band. So there should be states available, and number of states is basically this one, which actually means that I can measure the density of states of the material. Okay, how? Because how many states are available in my sample? The current which is passing from the tip to the sample will be proportional to the number of states available there, because metal has infinite number of, theoretically, infinite number of electrons. So if large number of electrons are going from the tip to the sample, this means that so many states are available there in the conduction band. If I am getting large number of electrons from the tip, which means that large density of state is there in the valence band. Okay, so like that we can actually measure the valence band density of states, conduction band density of states, and the density of state is very important for applications. Okay, because how many electrons you are getting outside, how many electrons can float to the material, all depends upon how many states are there in the valence and the conduction band, or HOMO-LUMO levels. Okay, without which it will be a useless material. Okay, so measurement of density of states we can clearly do depending upon the current, tunneling current of the instrument, okay, of the material. So this is what I said, this is called the IV spectroscopy. We just fit here, and this pen contains basically E minus V is taken as phi. So basically that E contains half of phi of S is the work function of the sample. This is the work function of the tip. So basically the tip work function we know because we use the platinum iridium tip. So we know the work function of it. So we know the voltage we applied to get this tunneling current. So it's a 0.5 volt, for example, or 1 volt. And from that we can easily find out what is the work function of the material. You should be careful here. Work function of the material will be local work function, because we are going to see only a few atoms. Okay. And if you change, when you are doing XRD, X-ray diffraction, you know that you are getting many peaks because it is a multi-crystalline or polycrystalline material. Which means that if you are doing work function on one crystal, and if you just move it slightly away, situation may be different there. Okay, you will get another work function corresponding to a different state or different crystallography. Okay, so you are not going to get an average work function. You are getting local work function. You are going to measure the local density of states. So it is not actual density of states of the material. It is local density of states. LDOS. Okay, local density of states. Also local work function. Okay. Okay, so this is what I was saying. So if the tip is positive and the sample is negative, electron will jump from sample to the tip, which means that we are mapping the valence band. Okay, and then we will get current like this. Now what about if there is a band gap? We don't get any current because there are no states, no electrons in the band gap. Okay, electrons are occupied here in the ground state. Conduction band is the excited state of electron. In between the band gap is there are no states, so we don't get any current if you are. So basically we are scanning from negative voltage to the positive voltage. Okay, so in certain area we don't get any current, which corresponds to the band gap. Okay, and the tip is here, and when the tip is there, again you will get current because tip is supplying electrons to the other side, which means that this current will correspond to the density of states in the conduction band. This state will correspond to the density of states in the valence band, and the distance between them, where there is no current, less current, will be the band gap. Okay. Suppose by doping or something you create some defects in the material, and suppose you have some states here, that also you can actually see here. Instead of zero current, there will be some current, and then it will go up. That also we can measure how many states you have created. Okay. So if I take just a derivative of this curve, it will look like this. Okay, just a derivative because zero constant derivative of constant is 0, and this is increasing, so you will get a peak like this. And this is how the local density of states will look like. And as I told you, this part will correspond to the valence band. This part will correspond to the conduction band. So if I tell you, so this is the valence band and this is the conduction band. And an actual example, okay, this is the density of states measured for zinc oxide doped with copper. Zinc oxide is an N-type material, right? When you put copper in it, it becomes P-type material. And we just say that, okay, it became P-type material. How do we know that? The 0 corresponds to Fermi level. Okay, so this is the valence band, and this is the conduction band, and this is approximately, again, locally, the band gap. Okay, and that 0 level is the Fermi level. Now you see Fermi level is close to the valence band. Okay, Fermi level close to the valence band is P-type material. Okay, and Fermi level close to conduction band is N-type. Like that, we can immediately find out what is the type of material. Okay, if I know that Fermi level is this close to the conduction band or LUMO level, and the Fermi level is there. From this difference, I can calculate how many doping is there, how many electrons are there. All those things now theoretically I can estimate. Okay. Last thing. Okay. Promise. There's a very new type of spectroscopy with the STM. Okay. Recently developing, and one of my PhD students is working on this. So this is called inelastic tunneling spectroscopy. This electron which are tunneling from tip to the sample, I mean, most of the 90% of the electron will just elastically tunnel. That means there is no energy change. It will just go through. But some electrons, what will happen is that while tunneling, if there is a molecule, it will excite the molecule. The vibration levels of the molecules will be excited. That means some electrons will transfer some energy to the molecule. That means they lose their energy. Those electrons will lose their energy. That actually we can see as, so you just simply take a tunneling current versus voltage plot. You will see some changes in the slope, and if you again just take di dv, differential of this one, wherever the constant is there, we will get a slope here, I mean a zero slope. So just the differential of that, the same plot here. Take one more differential, you will get a peak here. Okay, so this peak corresponds to vibration levels of the molecule. Okay, now how do we find out vibration levels of molecules otherwise? Either Raman spectrum, okay, you had yesterday. We can measure the phonon, right? Phonon levels and vibration levels we can measure using Raman spectroscopy, or we can use IR spectroscopy, FTIR. That actually excites the molecules' vibration levels, and we say that, oh, this is OH group, this is COH group. Okay, so those excited states we can measure using infrared, because the excitation energy comes only in the infrared region. That's why if you scan in the IR, infrared, these molecules will be excited, then we can see, oh, that is the level. But there is a problem with IR and Raman. Okay, what is the problem? To get an excitation, it has to be an optically allowed transition. Okay, all transitions are not optically allowed. All vibration levels will not be active in the optical regime. That means photons cannot activate some of the regimes of vibrations, but electrons can do all the vibrations. Okay, so here, if you do, I did not show any example here. If you take graphene or graphene oxide or any of these materials where there is a vibration, atomic vibration is there, we can do inelastic tunneling spectroscopy and we can find out what is the vibration levels. So even single molecule vibration levels we can do, that's the advantage. Okay, and all the vibrations which are not even optically allowed also can be measured. Okay, I think that's fine. Yeah, only conducting samples or single molecules. Okay. The limitations of STM, because we need to get tunneling current. Okay, because of that, getting a tunneling current is difficult from non-conducting samples. So conducting or single molecules, if it is non-conducting sample, it has to be single molecule or 1 or 2 layers only possible. To know what you see, you need to know it beforehand. Okay, what you are looking at. For example, if you are doing the electron tunneling spectroscopy, you have to first do a DFT calculation and see what are the vibration modes of the molecule, and then you come back. Otherwise, you will see that some noise is coming. That also is a vibration level. Okay. While measuring this spectroscopy, while measuring with STM, if somebody is passing by, tip will oscillate. You will get a tunneling current oscillating. Suddenly we think that that's a vibration level of the molecule. No. So you have to first do a DFT calculation and see what are the possible vibration levels of the molecule, how much energy is there for every vibration, and then you look back to the IV spectrum, IV characteristics, then you can identify the peaks. Okay. And by the way, even for molecular detection, okay, for now we are writing a patent on that actually, just submitted, that's why I'm openly telling. So for these biomarkers, right, for all diseases, cardiac diseases or neuro diseases, there will be biomarkers in our blood. We can actually detect even single biomarkers using IETs. Okay. That means if a person has Alzheimer's, suppose, very beginning stage. So if you, with a drop of blood, we can actually identify whether in 10 years he will have that disease. I mean, one doctor asked me, well, we want to know that because there is no cure for Alzheimer's. Okay. You are telling 10 years earlier to the guy that 10 years from now you are dead. Okay. So, but I mean, that's not the way we do research, right? I mean, maybe there will be a remedy in the future, but we can actually detect that, okay, very early using this, because this is a single molecular spectroscopy.